Hi, I'm Michael Shantz, and I'll be talking to you about the paper SoK Differential Privacy as a Causal Property, my joint work with Shayak Sin and Anupam Datta. The main takeaway from this work is that differential privacy is better understood as a causal property than as a statistical property about correlation, association, or mutual information. Recall that differential privacy is a formal property that an algorithm can have. It is designed to protect the privacy of people providing the algorithm with data points. The main result of our paper is to prove that differential privacy bounds the effect size of a person's data point on the output of the algorithm. It does not bound the correlation between the data point and the output, or how much information someone can learn about the data point from the output. If it seems odd that one can be bounded but not the other, remember that correlation does not imply causation. The counterpositive means that a bound on effect sizes does not bound correlation sizes. Our starting point for this work is a disagreement in the prior work about differential privacy. Authors disagree about whether differential privacy requires assumptions about the data to work. How can such a disagreement arise about a mathematical property? To answer this question, let's start with an example to understand what differential privacy provides. Suppose we are interested in figuring out how common a genetic mutation is by collecting medical information from people. Here, for simplicity, I show just two potential survey participants, Ada and Bob. To get them to honestly reply to our survey, we guarantee that the survey's output will be differentially private. Differential privacy ensures that if Ada drops out of the survey, the output won't change much. And the same holds true if Bob drops out of the survey. In more detail, differential privacy is a property that can hold of an algorithm. The algorithm consumes a set of data points and produces some output. Intuitively, the algorithm computes some statistic of the data set, such as the number of people with some disease. However, to have differential privacy, the algorithm must be randomized, for example, by adding random noise to the raw statistic. The randomization must be sufficient to ensure that the output will probably be the same if a single person's data point changes from one value to another value. More precisely, the distribution over outputs produced by the algorithm should only change by a small multiplicative factor. To show how this can work, let's return to our example and make it more concrete. Suppose that the output is a differentially private count of the number of people with a genetic mutation. The Laplace mechanism would be a natural choice for such a counting task. But to make our analysis more straightforward, we'll instead use one based on the randomized response mechanism, albeit computed by a single central database. This program takes a list of data points, each of which records whether a person is positive or negative for the mutation. To produce privatized data points, the algorithm looks at each data point one by one, and with a probability of 1/4, it flips the value of the data point. It counts up the number of privatized data points that are positive. We can calculate the probability of each possible output given that both Ada and Bob report having the mutation. For example, to produce a privatized count of 0 would require both data points to be flipped by the algorithm, which can only happen with a probability of 1 in 16. We can repeat this for the other possible outputs. Doing these calculations for the other possible inputs produces a table for all the inputs and outputs. Examining these probabilities, we can see that changing any one of the inputs changes the probability of any of the outputs by at most a factor of 3. This means that the algorithm has log 3 differential privacy. Okay, but what does this really get us? To approach this question, let's recall the mathematical definition of differential privacy. While mathematically fine, this definition isn't the most intuitive to those used to working with statistics over random variables. We can equivalently express this requirement using random variables and conditional probabilities. This highlights that the database and output are random variables probabilistically connected by the algorithm. We can also use a random variable d to model the single data point whose value varies. It's natural to try and simplify this comparison by jettisoning all the data points other than the one that varies in the comparison of probabilities. This would allow us to focus on the association between the changed data point and the output. This modified form of differential privacy has been called Bayesian or associative differential privacy, and has been promoted by several papers as what differential privacy is supposed to imply. The catch is that it's a strictly stronger property than differential privacy. To understand why, let's return to our example. Recall that we have Ada and Bob providing genetic information to a differentially private survey. Now let us add that Ada is Bob's mother and the mutation we're interested in is to mitochondrial DNA, which is only inherited from one's mother. This introduces a correlation between Ada's and Bob's data points. This correlation means that Ada's data point provides information about Bob's, and Bob's data point provides information about Ada's. In this case, the association between one of these data points and the output will be stronger than one might expect from differential privacy, since both data points will be providing information about the other. To make this more clear, let's first make the nature of the correlation precise. We can represent the context of the survey as a program showing exactly how the correlation arises. In it, we treat random variables, such as Bob's DNA, as the variables of the program. It shows that Bob's data point is determined by his DNA, which is determined by his mother's DNA. So Bob's data point will be equal to the value of his mother's, and the two will be perfectly correlated. In this setting, conditioning on just Ada's data point is the same as conditioning on both, since you can infer the second from the first. Given that, we can easily calculate the probability of seeing an output given just one of the inputs from the table we calculated earlier. What we find is that the two probabilities differ by a factor of 9, not just 3, since effectively two data points change between them, not just one. So, while the algorithm has log 3 differential privacy, comparing the probability of outputs when conditioning upon just a single change input involves a factor of 3 squared. Because of this, associative differential privacy implies differential privacy, but is strictly stronger. To get from differential privacy to associative differential privacy requires making an additional assumption. One assumption already suggested by our rewriting of differential privacy to use random variables is conditioning upon not just the changed data point, but all of the data points. This is called the strong adversary assumption, since it can be thought of as assuming that the adversary already knows the value of every data point except for the changed one. This assumption allows differential privacy to imply associative differential privacy, since it shuts down the double flow of information explored in our example. If the adversary already knows whether Ada has the mutation, learning whether Bob does provides no new information about Ada's status. A second possible assumption is that the data points are statistically independent of one another. While either assumption works, neither is realistic in many settings. How would an adversary know everyone else's data points? If the data points are independent of one another, how are they related enough to be worth collecting together? This state of affairs has led some prior work to claim that differential privacy implicitly makes one or the other of these assumptions. This claim has been controversial, with others disputing the idea that differential privacy requires either assumption or is broken without making one. They instead say that those making claims of implicit assumptions are trying to shoehorn differential privacy into fitting unrelated statistical properties. But if differential privacy is not such a statistical property, how can we think about it? Returning to our list of definitions, we could say that differential privacy is just the property we have on lines 1 and 2. However, this is disappointing. Differential privacy is typically explained as meaning that the output won't change much with or without your input. Lines 1 and 2 don't seem to capture this intuition since they refer to other people's data points as well, unlike associative differential privacy on line 3. It turns out that we can have the best of both worlds by switching from looking at associations or correlations to looking at causal effects. Here I'm using Pearl's do notation to denote that rather than conditioning upon the value of a single changed data point, we are instead looking at the effects of a causal intervention setting that data point to have a particular value. To make this precise, let's return to our example, represented as a program. We use assignments to represent causal links. Like assignments in a programming language, these links are directional, flowing from the right-hand side to the left-hand side. We can view conditioning on Ada's data point as getting to see the value of this variable. Seeing the value of this variable will tell you the value of other variables, such as Bob's DNA or the database. Conditioning upon the value of Ada's actual DNA will tell you the exact same thing since the data point's value is equal to the DNA's. However, this distinction becomes important if we consider causal interventions. Causal interventions correspond to disrupting the natural order of things as done in experiments. We model a causal intervention as an edit to the program, which fixes the value of the variable to a constant. In real life, editing DNA is much harder than editing a data point in a survey's records. However, with the way we are using a program to model causation, both interventions correspond to just editing an assignment statement in the program. This ease corresponds to the conceptual ease with which people consider counterfactual questions such as what would happen if Ada had a particular genetic mutation. Let's first consider setting Ada's data point to be a constant positive value. The intervention will flow down to other variables in the program, but it won't flow up to Ada's actual DNA. So looking at Ada's data point no longer tells us anything about her actual DNA, since the intervention broke the connection between the two. Alternatively, we could instead intervene on the underlying DNA itself. Intervening upon Ada's underlying DNA maintains the connection between it and the data point, which is causally downstream of it. Unlike intervening on Ada's data point, intervening on Ada's DNA would also flow down to Bob's data point, having two effects on the database. This difference explains why it's important to distinguish between the underlying condition and the data point recording that condition. We can represent this in our diagram as well. The causal effect of Ada's DNA, shown in gray, reaches every random variable in the diagram. The causal range of her data point, shown in blue, does not reach Bob's data point, despite them being correlated by having a common cause. Furthermore, Bob's data point does not affect Ada's. This is why a causal interpretation of differential privacy works. It's not a property about the underlying conditions measured by the data points. It's a property about the data points as inputs to an algorithm, and those inputs do not affect one another even when they are correlated. So while a data point's correlation might be twice what you expect, its effects won't be. The consequence of this is that while differential privacy does not bound how much an adversary can learn about a data point from an output, it does bound the effect size of the data point on that output. In particular, it bounds the effect as measured by the difference of log probabilities. With this measure of effect size, we can make precise our explanation of why disagreement exists in the prior work. The essence of the disagreement is the feeling that differential privacy should be bounding the size of some relationship between each data point and the output. Without a causal understanding of differential privacy, it's natural to assume that the relationship is correlation. However, differential privacy actually bounds the effect size instead. That this causal bound does not imply a bound of correlation is roughly equivalent to the maxim that correlation does not imply causation. So the perceived shortcoming of differential privacy is related to a well-known confusion. The measure of effect sizes used by differential privacy is elsewhere called relative probabilities, and it can measure the causal effect of any variable on any other variable. Differential privacy is an upper bound on this measure across all the possible data points, pairs of values they can take on, outputs, and distributions over other data points. Like differential privacy, relative probabilities compose additively in the exponent. We can use relative probabilities to make precise variations of differential privacy, such as local, group, node, or edge differential privacy. Doing so moves us from semantic debates about what counts as a data point to specifying which random variables effects are bounded. While information is more related to correlation than to causation, we do not mean to suggest that differential privacy is unrelated to information. With differential privacy, each data point has a limited effect size on the adversary's knowledge. This provides a causal perspective on semantic privacy, a property from prior work. In addition to explaining the disagreement in prior work, the realization that differential privacy is a bound on effect sizes explains why differential privacy has found applications away from privacy, such as in non-discrimination, data exploration, and secure machine learning. Causation cuts across science and engineering tasks, and we should expect it to appear in many applications. While we have explained what differential privacy provides, the question remains as to whether differential privacy or associative differential privacy better captures what we mean by privacy. Each has its limitations. While associative definitions bound what an adversary can learn, they are essentially impossible to provide and disallow studies that greatly benefit society. For example, consider a study showing that smoking causes cancer. Despite the great importance of such a study, it may be disallowed under an associative notion of privacy. Indeed, after knowing that smoking causes cancer, you know that anyone you see smoking has an elevated risk of cancer. However, that holds regardless of whether a smoker participated in the study. On the other hand, causal definitions, like differential privacy, focus on preventing someone's participation in a study from causing information leakage, and therefore may be sufficient to encourage participation in the study. These properties are also easier to provide simply by adding noise. However, they allow studies of questionable value, such as the gaydar study, which trained a machine learning model to predict who is gay from photos. It is debatable whether this study violated privacy or some other value. Either way, we do not expect a complex normative topic like privacy to be reduced to either a simple associative or causal property. Thank you for your time.